Hello everyone. Let us now discuss the working of photodiode, light emitting diode and solar cell. Photodiode is a PN junction which works when light falls onto it. This is a symbol that we use, light falling on a diode. How does it work? It's a PN junction actually. We have a depletion layer. When radiations fall onto it, PN junction, if the incident radiation has energy which is more than the band gap, then electron hole pairs will be produced. And if electron hole pairs are produced in this depletion layer, what will happen? The electrons will move to the n side because here we have positive charge, here we have negative charge. In a depletion layer, electric field, potential barrier. So whenever any electron hole pair will be produced, electron will move to this side and hole will move to this side. Same which happens in case of drift current actually. It is also drift current. So we are increasing the value of drift current. And we connect the battery like this. Positive connected to N side. So it is in reverse bias. Drift current will be increased. So if we connect any ammeter here, the reading will increase. More current will flow in the circuit. Now what will be the use of it and why are we connecting it in reverse bias? It is in reverse bias because the change in current may not be too large. If we connect the PN junction in forward bias, then large current flows through it. In reverse bias, very less current flows through it. So whatever changes are there in the current, they are not very large. So if we connect the diode in forward bias, those changes will go unnoticed. If the current is flowing in milliamperes and the current changes in microamperes, so it will not be very significant. So that's why we connect the diode in reverse bias. So now whatever changes are taking place, they are large. So fractional change is large in case of minority carriers. And that's why it is connected in reverse bias. And use, now see, current is depending directly on the light. So these are used for detection of optical signals. That is the most important use of photodiode. So they can be used in counters also, electronic counters. So whenever, see, it is whenever light is falling, current is increasing. So whenever we have to control something on the basis of incident light, then it can be used. So wherever we have to identify an optical signal based on its intensity, we can use photodiode. Same way, we can use it in counter. Whenever light is obstructed, current is decreased. Whenever light is falling, current is increased. So it can somehow be related to counting. I plot graph between the voltage applied and the current. Then it is reverse bias. So it will be like, if I increase the intensity, current will be increased. So I2 more than I1. Same way, if more intensity, then current will be increased further. Okay, next is light emitting diode. It is just opposite of photodiode actually. Light emitting diode is, we connect it to a electricity source and then it gives us light. The symbol is also like this. It is shown to emit radiations. a PN junction depletion layer connected in forward bias. We know that whenever a PN junction is connected in forward bias, current flows through it. Now when the electrons are moving from N side to P side, on N side the electrons are majority carriers and they are in the conduction band. But when they combine with the holes in the P region, holes are in valence band. So it means the electrons on N side in conduction band have more energy than the holes which are present in the P side. Conduction band and valence band. So whenever one electron is combining with the hole, it is coming from conduction band to valence band actually. So its energy decreases and this energy is released in the form of radiation. When we are using pure silicon, then the wavelength of this radiation, this falls in infrared region. So if we want to get light using LED, it's important that we should select the materials in such a way that this band gap, it is of the range, it lies in this range of wavelength, which is a range for visible light, has energy which is equal to the energy corresponding to this value of wavelength. Then we will get light. Gallium arsenide is the best material and the most common material that is used for making LEDs. The light that is obtained is almost monochromatic. LEDs are very cheap, they are very small, they work at low voltage, they don't require too much of careful handling actually, and the size is also very small. So these are all advantages of LEDs. And the most common use of LEDs is we use them as indicators in various music systems, radios, televisions. We use even in remotes. So they are the most important and significant uses of LEDs. If you want to plot a graph, so this is forward bias. So VI graph. But depending on the material, knee voltage may change. It's a solar cell in which we have N type, here P type, so again a PN junction. The base of it has metallic cap and the top of it again a metal but in the form of grid, so as to allow radiations to fall on the junction. Now when the radiations fall onto it, on this junction, again a number of electron hole pairs are produced due to the electric field at the junction. N side we know has positive charge, P side has positive charge. So electrons will move to N side and positive charge will get collected holes on P side. So this base becomes positive and this as negative. Again the condition is that the incident radiation should have the value more than the valence, more than the band gap to produce electron hole pairs. So negative and positive. Now it's a PN junction again, and it is the depletion layer. Now when it is connected in any circuit. Now one important difference is that here we will not use any battery because solar cell itself is to be used as a source of voltage. So it will be connected across any resistance. P side is plus, this is minus, so this will be the direction of current. Usually, otherwise, how does the current flow? Current flows like this in a diode. But here we are taking the current from the cell. We are not supplying any external current to it, and we are not connecting it to a voltage source. We are taking from it. So it means if I plot a graph, VI graph, initially the voltage is maximum. We call it open circuit voltage. And when I connect it to this resistance, current starts flowing through it. And when the voltage decreases now, it is plus, when the current is flowing, electrons are moving in this direction, charge here will decrease, current will increase. We call it short circuit current. So this will be the VI graph. It will be in the fourth quadrant. We are taking current from the cell, not giving it. So it's all about photodiode, light emitting diode and solar cell. In photodiode, light falls onto the PN junction, electron hole pairs are produced. This causes a change in the drift current. So it is used to detect the optical signals. In light emitting diode, it is connected to a voltage source. When electrons are moving from N side to P side, they are combining with the holes. The excess energy is released in the form of light, provided the band gap is same as of visible light. In solar cell, radiations fall onto the junction, electron hole pairs are produced, they are collected on N and P side, and then this is used as a voltage source.